Hello students, last lecture we have discussed about the types of electrical current. In this type, we have briefly discussed about the type of DC current. Today's lecture we have to discuss another type of electrical current, that is AC current. That is AC current means alternating current. This alternating current. This is the one of type of electric current. In this chapter, we have to discuss briefly about the alternating current, means AC current. Okay, there is a difference between AC current and DC current. So first of all, we discuss about the difference between AC current and DC current. In case of AC current, what is by AC current? The current which changes its magnitude, polarity as well as its direction is called as an AC current. That means the behavior of the AC current is like that. In this behavior, we have seen this current or the electrical quantity which changes its direction, then magnitude as well as its polarity. Okay, that means the current which changes its magnitude, direction, and polarity is called as the AC current. In case of DC current, the current which does not changes its direction, polarity, and magnitude is called as a DC current. This is the on y-axis is the voltage or current quantity, on x-axis and on x-axis we draw here a time. Okay, that means with respect to time, this current does not changes its magnitude, direction as well as polarity. Then this current is called as a DC current, and the current which changes its direction, magnitude as well as polarity is called as a AC current. Okay, this is the major difference of AC and DC. Okay, another difference is that in case of DC, use of transformer is not possible. Okay, use of transformer, that means excimer is not possible. Okay, use of transformer is not possible in case of a DC circuit. In case of AC circuit, whereas in case of AC circuit, the use of transformer is possible. Okay, use of transformer is possible in case of a AC circuit. The machine design of AC circuit is very easy, whereas the machine design of DC circuit is not easy. Okay, then generation of AC is also easy, then generation of DC is not easy. Then next, the distribution efficiency of an AC circuit is very high as compared to AC circuit. The efficiency of DC circuit is lower. Okay, this is the major difference between the AC circuit and DC circuit. AC circuit shows more advantages. Because of that, we use AC circuit instead of the DC circuit. Okay, there are different types of AC circuit depending upon the nature of the waveform. Okay, there are three types of AC circuit depending upon the nature. First type is triangular waveform. Triangular waveform, whose shape is like a triangle. Triangular waveform. Second is square waveform. Square waveform. And last one is a sinusoidal waveform. It's called sine wave. It's also called sine waveform. Okay, these are the different types of AC circuit depending upon the nature of the waveform. That means here three types of nature. Waveform shows the three types of nature. First is the triangular nature, second is the square nature, and third one is the sine nature. Okay, this diagram shows sine waveform, then triangular waveform is like that, and last one is a square waveform. The shape of square waveform is like that. Okay, that means square waveform shows by square waveform, triangular waveform shows by triangular waveform, and sine waveform shows by the sinusoidal waveform. These are the types of AC waveform. Okay. Then next is the generation of AC waveform. Already we have discussed about the generation of AC waveform by the singleton alternator. If the single coil of alternator is used, then we know the generation of the AC waveform. Now the voltage equation of the waveform. Okay, the voltage equation for the waveform is at any instant V of t equals to Vm sine omega t. Okay, voltage equation for the sine wave is, or the voltage equation for the AC is V of t, instantaneous voltage V of t equals to Vm sine omega t. Here Vm shows the magnitude of the voltage or peak value of the voltage. Okay, Vm means max value or peak value of the voltage, whereas omega t shows the angular displacement. Okay, angular displacement. We know that omega equals to 2 pi. Okay, 2 pi. Then this is the value of the omega, 2 pi f0. Okay, value of the omega is 2 pi f0. That means voltage equation becomes V of t equals to Vm sine 2 pi f0t. Okay, 2 pi f0t unit is volt. This is the voltage equation. Whereas the current equation can be write as I of t equals to Im sine 2 pi f0 t. Unit is ampere. This is the current equation for the AC in case of a sinusoidal quantity. Okay, this is the current equation and voltage equation of the AC quantity. Now we have to discuss about some important definition related with the AC waveform. Related with the AC waveform, the first definition is the waveform. First definition is the waveform. To understand this definition, we draw here waveform. By using this waveform, we can easily understand the different definitions. So, this is the magnitude or peak value of the waveform denoted by Vm or Im. Magnitude here, pi angle here, 2 pi angle. Okay, this is pi by 2 angle. Okay, the first definition is waveform. Okay, then what is a waveform? Waveform is the graph of magnitude of an AC quantity. Okay, what is my waveform? Waveform is the graph of various instantaneous value. If we consider the various instantaneous value of AC quantity and draw it by a smooth line, then the nature we found, this nature is called as a waveform. This nature is called as a waveform. If the shape of the waveform is like that sine shape or a sinusoidal shape, then the waveform is called as a sinusoidal shape. If the shape of the waveform is triangular shape, then the waveform is called as a triangular waveform. If the shape is square, like a square, then the waveform is called as a square waveform. Okay, that means the waveform is the graph of magnitude of AC quantity against the time. Graph of AC quantity against the time is called as a waveform. Okay, next is a cycle. Okay, second definition is a cycle. What is by cycle? Cycle means half positive and half negative. Same quantities, half positive and half negative, is called as a one complete cycle. The angle of one complete cycle is 0 to 2 pi radian. Means 2 pi radian means 360 degree. Okay, angle of the cycle is 360 degree. One cycle equals to 360 degree angle. Okay, then next is a time period. Okay, next is a time period. What is my time period? The time taken to complete a one cycle. Okay, the time taken to complete one cycle is called as a time period. That means this is our time period. It is denoted by T, and time is always measured in seconds. Okay, time is always measured in seconds. Then the next definition is a frequency. Okay, okay. Then what is my frequency? Number of cycles. Okay, number of cycles. The one cycle starts from 0 to 2 pi. Number of cycles completed in 1 second. Okay, what is the frequency? Frequency means number of cycles completed in 1 second is called as a frequency, and frequency is denoted by F, Frequency is denoted by F, and measures always measured in hertz. Okay, always measured in hertz. Indian standard frequency is 50 hertz, whereas US standard frequency is 60 hertz. Okay, frequency is number of cycles completed in 1 second is called as a frequency. Then next is the amplitude. Okay, next is the amplitude. What's the amplitude? Amplitude is the maximum value of a AC quantity. Okay, maximum value of AC quantity is called as a magnitude or a peak value. Okay, it's called as an amplitude also. It is also called as an amplitude. It is also called as a magnitude and a peak value. Okay, all these are the same quantity: magnitude, peak value, and amplitude. Okay, next is a effective or RMS value. Then what is the definition of RMS value? An AC current is equal to the steady state or a DC current that is required to produce the same amount of heat as produced by the AC current, provided that by the same resistance. Is called as a RMS value. RMS value is denoted by R dot M dot S. Okay, and the RMS value of voltage is denoted by VRMS, and RMS value of current is denoted by IRMS. Okay, the value of RMS are always constant. Okay, then what is the RMS value? RMS value is the 0.707 into max value of voltage. Then RMS value of current is 0.707 into max value of the current. It's called as the RMS value of the current. This value is always constant. Okay, this value is always constant. This is called as a VRMS, and this is called as a IRMS. Okay, this is called as a IRMS. Then next is a average value. Please denote. Okay. Next is the form factor. Form factor is the ratio of RMS value to the average value. Okay. Form factor is the ratio of average value to the RMS value. Form factor is denoted by KF. Okay. Form factor is denoted by KF, and the value of the form factor is always constant. That is 1.1, and it is a unitless quantity. That means KF is equals to 1.11. Okay, KF is equals to 1.11. This is the value of form factor. Then next is the crest factor. It is denoted by Kp. Okay, crest factor is denoted by Kp, and the formula for the crest factor is the ratio of peak value to the RMS value. Okay, it is the ratio of peak value to the RMS value, and the value for the crest factor is 1.414. Okay, value for the crest factor is always Kp equals to 1.414, and it is also constant value. Okay, it is also constant value, as well as it is also a unitless quantity. Okay, what is the value of Kp? Kp value of the Kp is 1.414. Okay, repeating. Then next is a phase angle. Okay, Next point is a phase angle. Next is a phase angle. Okay, what is the phase angle? The phase angle means the conductor making angle with the reference line. It's called as a phase angle. Okay, conductor making angle with the reference line is called as a phase angle. Okay, this is called as a phase angle. Okay, the phase angle always rotate in anti-clockwise direction. Okay, phase angle always rotate in anti-clockwise direction. Then the question arises that what is meant by phase or what is meant by the phasor. Okay, question arises what is meant by the phasor. What is meant by phasor? Phasor is a straight line. Okay, phasor is a straight line with an arrow mark on the one side. Okay, phasor is a straight line with arrow mark on the one side. Okay, arrow mark on the one side. Then the the length of the phasor. Okay, this is the length of phasor. This length represents the magnitude or the maximum value of the quantity, AC quantity or DC quantity. This length indicate the magnitude of the AC quantity. That means if we draw here this waveform, this is the magnitude of the. Suppose this is the waveform of voltage. This is the magnitude of the voltage. Then this magnitude indicates the length. Okay, this magnitude indicates the length, and this angle indicate the angle made by a conductor with the reference. Okay, this angle indicate the this angle indicate the angle made with reference by a conductor. Okay, this is called as a phasor, and this is called as a phasor and phase angle. Okay, then the next concept is phase difference. Okay, next concept is phase difference. So what is in the phase difference? The angle between the two AC quantity. Okay, again the question arises that can we write or can we represent the two phasor at a single sinusoidal waveform? Yes, we can. We can draw the phasor of two different quantities, but here one important condition is that we can draw two phasor for a different quantity if and only if their frequencies are same. Okay, if the frequencies are same, then we can draw the two quantity phasor. Okay, if this is the reference phasor made by the voltage or waveform made by the voltage, if the current start from 0 and crossover point of the current is same, that means frequency of current and voltage, if the frequency of current and voltage is same, okay, this is the frequency, this is the waveform for the current. If the frequency for the voltage and current is same, then we can draw both the phasor at a time, current and voltage phasor at a time. So phasor of the voltage is like that V, and there is no phasor difference between two lines. Therefore, phasor of the voltage is also on the same line. Okay, that means both are in phase. Both are in phase. Okay. Then next is the type of phase difference. Next is the type of phase. If there is a phase difference between two electrical quantities, then this is the phase difference phi. We can write down as a, we draw here reference line voltage, and another phasor we can draw by taking this phase difference. So the phase difference is phi. Then this is the phasor for the current phi. This is called as phase difference. तर आपण म्हणणार आहे फेज डिफरन्स. काय म्हणणार आहे आपण? फेज डिफरन्स. जर दोन इलेक्ट्रिकल क्वांटिटीज सेम फ्रिक्वेन्सीच्या असतील तरच आपण त्यांची फेजर डायग्राम ड्रॉ करू शकतो. ओके, इफ अँड इफ the frequencies of the both electrical quantity is same, then only we can draw the phasor diagram. तरच आपण त्यांची काय करू शकतो? फेजर डायग्राम ड्रॉ करू शकतो. ओके, नेक्स्ट इज द टाइप्स ऑफ फेज डिफरन्स. नेक्स्ट इज द टाइप ऑफ फेज डिफरन्स. Okay, There are three types of phase difference. First is a leading phase difference. Leading. Second is a lagging. And third one is a in phase. Okay, third one is the in phase. Third one is the in phase. Okay, first is the leading. First is the in leading. If the angle phi, if the angle phi is positive, okay, if the angle phi is positive, then it is called as a leading phase difference. Okay, if the angle phi is positive, then it is called as a leading phase difference. If the angle phi is negative, then it is called as a lagging phase difference. It is called as a lagging phase difference. If there is a no phase difference, there is a no angle phi generated between the voltage and current or two electrical quantities, then it is called as a in phase. Okay, it's called as a in phase. So this is called as a leading phase. That means current lead voltage by angle phi. That means phase difference is positive. Next is lagging phase difference. That means current lag behind voltage by phi angle, and this one is the in phase. That means there is a no phase difference between current and voltage. It's called as a in phase. It's called as a in phase. Okay. Now behavior of AC circuit. Next concept is behavior of AC circuit. We know that all the AC circuit are made from three basic elements: resistive circuit, inductive circuit, and capacitive circuit. Okay, these are the three important component of the AC transmission line. AC transmission lines important components are resistance, inductance, and capacitance. Okay, now the behavior of AC circuit we can observe by considering the AC circuit with pure resistive, AC circuit with pure capacitive, AC circuit with pure inductive. Means AC circuit with pure resistance, AC circuit with pure capacitance, AC circuit with pure inductance. Okay. First of all, AC circuit with pure resistance. AC circuit with pure resistance. Now, this circuit consists of only resistance. Therefore, we draw here single resistance and connected across a single phase AC supply V. This is the resistance R. The equation for the voltage is Vm sine omega t. If the supply is turned on, then current I starts flowing to the resistance. Okay, current start flowing to the resistance. If the supply is on, because due to this voltage, the current starts flowing to this resistance. When the current start flowing to the resistance, then here a voltage drop happens across the resistance. This voltage drop is called as a VR. Okay, VR means the voltage drop across the resistance. Voltage drop across the resistance. Then the equation for the supply voltage is given by V equals to Vm sine omega t. Okay, supply voltage V equals to Vm sine omega t. Then the voltage and current equation for the pure resistive circuit is given by, this is the voltage equation, and current equation I is equals to Im sine omega t. Okay, this is the current equation. I equals to Im sine omega t. If the current flowing through the resistance, then voltage drop happens across the resistance. In case of resistive circuit, by observing the voltage equation and current equation, we observe that there is a no phase difference between voltage and current. Therefore, the phasor for the voltage and current is like that. Voltage and current are located on the same line. So if there is no phase difference, then the phase is called as a in phase. Okay, then the phase is called as a in phase. That means the waveform for the resistive circuit is like that. If you consider this waveform as a reference line, this is the voltage V equals to Vm sine omega t. Vm sine omega t. There is no phasor difference between voltage and current. So the zero crossover of current and voltage is same. Therefore, the diagram, phasor diagram look like this way, and the equation for the current is I equals to Im sin omega t. This is the phasor diagram of pure resistive circuit. This is the voltage diagram, phasor diagram of pure resistive circuit. Okay. Now the main concept arises. What is my impedance? Okay. Impedance is the combination of resistance, capacitive, inductive reactance, and capacitive reactance. That is, it is a combination of I, comma XL and XC. Is called as a impedance. Now the impedance equation. What is the impedance equation in case of polar? In case of rectangle form, Z is equals to R plus J of X. Here, the term is only resistive. Inductance and capacitance are absent. Therefore, the value of Jx is 0. Therefore, the value of impedance in case of a resistive circuit is Z is equals to R only. And the average power consumed by this circuit is RMS value of voltage into RMS value of the current, means V into I. This is the average value consumed by the pure resistive circuit. Okay, this is the pure resistive circuit. Next is the pure inductive circuit. Okay, next is the pure inductive circuit. Now, in case of pure inductive circuit, resistance and capacitance are absent. Then let a pure inductor L is connected across a voltage source. Pure inductor is connected across a voltage source. V equals to Vm sin omega t. Here is a pure inductance. If the supply is connected, then current I start flowing through the pure inductance. Then voltage drop made across the inductor is called as a VL. Okay, voltage drop is considered as a VL. Okay, then the equation for the current is, okay, voltage equation is V is equal to Vm sin omega t. Now the current equation is I is equals to Im sin omega t minus pi by 2. Okay, current equation is Im sin omega t minus pi by 2, because in case of pure inductive circuit, the current is lag behind the supply voltage by exactly pi by 2 radian or a 90-degree angle. So the voltage equation is Vm sin omega t, whereas the current equation is Im sin omega t minus pi by 2. Okay. Now here the phase difference is, pi by 2. Phase difference is pi by 2. Therefore, we draw here waveform like, suppose this is the reference voltage waveform. Now the current waveform is lag behind voltage by pi by 2 radian or pi by 2 angle. Therefore, the current waveform start from the 90 degree. Current waveform start from the 90 degree, and there is a phase difference between voltage and current is phi. Phi is equals to pi by 2. Okay, phi is equals to pi by 2 or 90 degree. Okay, this is the voltage equation V. This is the waveform for the current I equals to Im sin omega t minus pi by 2 degree. Now the phasor diagram. Okay, if we draw voltage, if we draw reference as a voltage V, then by the voltage equation, we observe that current is lag behind voltage by pi by 2 degree, pi by 2 angle. Therefore, the current waveform is lag. Current waveform draw inside the downward direction by angle pi by 2. This is the current I and this is voltage V. This is the phasor diagram for inductive circuit. This is the phasor diagram for inductive circuit. Now, impedance. Okay, what is the impedance? Impedance is the combination of R plus R and XL and XC. Formula for the impedance is Z is equals to R plus JX. Now here circuit is pure inductive circuit. That means here only XL is present. Okay, here only XL is present. XC and R are absent. Therefore, Z is equals to J of XL. This is the impedance equation for the pure inductive circuit. Okay, this is the impedance equation for the pure inductive circuit. The value of R is equals to 0, whereas the value of X is also equals to 0. Therefore, Z equals to J XL, and average power consumed by the inductive circuit is P average equals to 0. Okay, P average equals to 0. Now the last is pure capacitive circuit. Okay, last is a pure capacitive circuit. Okay, are you getting this point? If you have any question, you can ask me on WhatsApp. Now, pure capacitive circuit or pure capacitance in AC circuit. Suppose a pure capacitance C is connected across the source of V is AC source of V equals to Vm sine omega t. A pure capacitance C is connected across the voltage source of V is equals to Vm sine omega t. If the supply is on, current starts flowing through the capacitance I, and due to the current, there is a voltage drop across the capacitance, which is denoted by the Vc. Okay, this voltage drop is denoted by the Vc. Now, the voltage equation is V is equals to Vm sine omega t. For the current equation, we observe that when the current is flowing through the capacitance, pure capacitive circuit, the current is always leading by 90 degree, which is of a pure capacitive circuit. That means current equation is made I is equals to Im sine omega t plus pi by 2. Okay, Im sine omega t plus pi by 2. That means here angle is pi by 2 plus pi by 2. That means the phasor difference is leading phase difference. Okay, phasor difference is leading phase difference. That means if we draw the waveform, suppose this is the reference voltage waveform, then the current waveform is lead by 90 degree. Okay, current waveform is lead by the 90 degree. So the current waveform is look like this way, and there is a phase difference phi equals to pi by 2. Okay, this waveform is voltage waveform, and this one is for the current I waveform. Okay, current is lead by pi by 2 degree. Therefore, the phasor diagram we can draw here. If suppose this is the voltage waveform, then by observing the voltage current equation, we know that the phase pi by 2 is leading with the voltage. Therefore, we draw here phasor in upward direction by phase angle phi equals to pi by 2 degree. Okay, phase angle phi equals to pi by 2 degree. This is the waveform for the waveform for the this is the waveform for the pure capacitive circuit. This is the waveform for the pure capacitive circuit. Phasor diagram for the pure capacitive circuit, and this is the waveform for the pure capacitive circuit. Now, impedance equation. Okay, we know that impedance equation Z is equals to R plus JX. Okay, now here XL is absent, X is also absent. Sorry, R is also absent, and we know that the formula for X is equals to XL minus XC. Value of XL is equals to 0. Then what's remain? XC. X is equals to minus XC. Therefore, the value of impedance Z is equals to minus XC. Okay, minus XC. So what remain here? Z is equal to minus XC. Okay. Now the last is average power consumed by the pure inductive circuit is also 0. Pure average power consumed by the pure capacitive circuit is always 0. That means PAV is equals to 0. PAV equals to 0. This is the behavior of AC circuit in pure resistive circuit, pure capacitive circuit, and pure inductive circuit. Okay. Remaining part we will conduct in next lecture.